So my main video is in the section following, just to let you know, as usual, download links for both drawings are available below this video. Hi and welcome. So this lathe project came about because I wanted to turn this shaft. It's a piece of aluminum and it seems straightforward, except that it's long and it sticks out the other end. So I could just turn it as is, but if this wasn't perfectly balanced, you'd get wobble. And it's an incredibly long lever arm for the rotation point, which is the jaws right here. So it's going to want to make this move ever so slightly. In addition, if it got crazy enough, it could damage the inside threads of this where it's designed for a lever pull collet changer. So my solution was to experiment with some metric reverse threads, left-handed threads, and I made this piece, which is a traditional solution for the problem. It is called a spider, a lathe spider, and its job is simply, after I get it tightened on here, its job is simply to help through these adjuster screws. I've actually ordered some set screws with nylon bushings, but its job is to help keep the stock centered so that it can't bang around and damage the inside of this threaded tube and won't affect the performance on the other side. So now it's kept in place. This rotates with the head, so I put the head neutral, see it rotates. And here's one of my problems with this design. It's a very common spider design, but you've got these screws sticking out and they're spinning, and man, doesn't that just beg to have something get caught in it and wrapped around it? Seems like a really bad idea. Also, another negative with this design is I used the threads because I wanted to try making threads. I used the threads that were built into the spindle and built this piece to go inside. So this is 1.5 inches. The spindle clearance is 2 inches, so I've just wasted 1/2 inch. I've got another design that I'd like to build which fits over the outside of this. And it's just going to use set screws with nylon bushings to use friction to hold it in place. And I'll make it a pretty close fit to this, but you may at first worry a little bit, like, could it pop off? But I don't think that's really an issue because there's not a lot of force axially here. There's radial force, which is what I'm trying to control, and it'll do just fine job of that. Anyways, that's my idea, and we're going to give it a shot, so wait and we'll build that next. Alright, so next we're going to dimension the outer part of this, and then we're going to drill and bore the inside lastly. Start with 100,000. I think I need to increase the speed rate. So little did I know, but this project is giving me ample opportunity for playing with speeds and feeds. So here I'm turning the outside dimension of the part. The only critical dimensions of the whole part are the inside diameter on this side, because that has to slide over the spindle of the lathe. All the other measurements can be rough. Measure a couple things. I want to change the feed rate. Let's jump hugely. Okay, whoa, what a mess. Okay, adjusting feeds and speeds here. We're going to go for another 100,000th byte. I've increased the feed rate to 10 thousandths per revolution. Maybe now the chip breaker will start working properly. That's better. Night and day. Another 50. So smaller byte with same feed rate, chip breaker is no longer working. Okay, let's take a measurement. Still coming at me, but at least the chips are breaking at higher rates. The new Shar's 12-inch that I got. Probably. This isn't a critical dimension, so I don't need to break out the micrometers. So 3.152. So I've got 150 thousandths to go. So we'll do 125,000. See how that works. Beautiful, really. Alright, let's take a measurement and come back. What a mess, though. Finish is surprisingly good. So 14 thousandths off. So let's slow that feed rate down and take the last 14. We're going to go back. We're going to have little hairs everywhere. This outer dimension is not critical at all. The inside boring dimension will be. Scratching up my surface. Thank you very much. Okay. Should be good. Chamfer an edge. Now I think we can bore some holes. I'll have to come back and chamfer this part when I can get in there. Let me flip it around. Alrighty. Alright, so we're going to start here and drill out most of the extra material at the center. I'm not going to bother center drilling. We're just going to drill out most of the material and finish by boring for accuracy. initial holes will be all the way through. So this is a high helix drill bit, so it's designed to get rid of a lot more material for aluminum and other soft materials. Might have pushed it a little bit hard there, but it actually does really well. I thought maybe I'd get it all in one go. Loading up quite a bit. I guess it is really deep, so I can't fault it too much. Oh, that's why. Loaded up a little bit on the end there. And we're through. It's always that last bit, isn't it? Alright, now half inch. Ultimately, we need to bore out 2 inches out of the center. All the way through, and then somewhat larger. I'm transitioning here from one drill bit to the next, so you don't have to watch all of the drill bits cut all the way through. And through. From here, I think we bore the rest. That's 1.5. Now let's go with this one for now. Let's see what this one does. So this is boring in almost 3 inches, and the carbide insert is not an aluminum cutting insert, so once you go deep there's really not a lot of places for the string to go. It's quite a mess, and it's not making chips, so I guess you see the results. Wow, that just scraped the daylights out. It was such a beautiful finish until the bee's nest there. Wow, that's something. Maybe too big a bite. Here's 100 thousandths at a high feed rate. going to try and keep the feed rate high but slow the RPMs down some. Let's see how this one works. Did okay. High feed rate made a terrible finish. This isn't a particularly sharp point either. I think we're going to follow up with a cutter actually designed for aluminum. So we're using a much lighter boring bar for finishing. This actually has an aluminum insert on it. Slowed up the feed rate. Presumably for a better finish. Still can't get the chips to break right though. Okay, now we got a nice big fur ball burnishing the inside there. That's awesome. Well, it's a hell of a lot better finish than I had before. Let's see where we're at. Again, not even a little bit critical size. Thousandths away. Okay, we're going to take the whole 12. Let's even go faster, see if a little bit more speed improves things. A little lube to test finish. Alright, let's give it a go. Too much speed for this much stick out, I'm guessing. Okay. So we should be at dimension now for the full through bore. Yep. So I'm setting my depth here, setting my Z-axis stop here, and then we're shooting for 2.5 inches internally. 2.56 to be exact. So we got quite a ways to go, half an inch. So let's try this. Set our 0 here. Yep. 250. I'll leave the last hundredth for later. Look at that mess. Yeah, so I definitely have some issues with chip breaking on this aluminum. It's just not working out so great. All right. Okay. Let's Do another 100 thousandths. Okay, chamfer done. Okay, this is the back of the lathe here, and let's see how that fits. Nice, very nice fit. Just going to put it back in the chuck and relieve these two edges, and then it's off to the mill to thread and tap. Okay, so the first job getting this on the mill with the rotary table is to, well, first I had to tram in the rotary table, which I didn't show, and now I'm tramming in the part. Oops. And I've gotten it pretty close. I mean, we're just drilling some drill holes here. Let's see if I can get that a little better. Okay, that'll definitely do. Alrighty, so now, matter of finding the center and drilling and tapping some holes. Okay, so to find center on the hole part, I'm holding this handheld, sorry about that. What I did was, since it's not a critical value, I took a shaft that I know is straight and hardened, and I just brought the part over until you could just see, focus, until you could just see the light go away like that. So finding the absolute center of the overall part, it's not ultra critical, it's just where the screws are going to go. If I had to do a more accurate job, then I would have to come up to a much more creative solution than this. My center finder I don't think will reach this far down a round part like this, so I use this method instead. And so you go to the one side, you set your DRO to 0, go to the other side, tell your DRO to go half that distance, that factors out whatever diameter this is and finds the center. So that's what I did. Okay. Move an inch. Drill. intersync. Prepare to tap. Sure I get the speed on snow. Plenty of lube. Okay, for the final assembly, here we are. So one of the things I was shooting for was to minimize the amount of stick out that any of the screws would have. A lot of these have the screws sticking out. My goal, the reason why this is so thick, was to make the stick out minimum so that it wouldn't accidentally catch on something and drag it into the device. Okay, so there we are. Measurements of these screws that they had. 5/16 did not include the brass bushing that sticks out apparently. And so if I don't want it to protrude in, I'm going to have to do something about that. Maybe file down the brass bushings a little bit just to get a little more thread in there. But let's see how this fits. Anyways. Alright, so when I ordered these from McMaster-Carr, they spec'd the height not including the insert, which I thought they were including. So I have to take some material off these so that I get enough threads to bite in this. So to hold them, what I'm doing is I found a nut and I'm threading this into the nut, and then to stop it from spinning, it's hard to do handheld here, I'm just backing it up with a bolt same size. Then I pop it in the vise and file it down. Alright, so here's final assembly and final product. Just pop this on, and then got to put this in neutral here so I can rotate it. Well, it's really snug. It's actually really good. Okay. So you show snug, and there you go. So let's stick a rod in there and see what we can get, see how it works. So again, we just there you go. So now they're all gently touching, which holds this in place. And when the lathe turns, this will turn with it. so that this will be supported and not wobble around, and that's the point of a lathe spider. Okay, so here it is working. This is the longest piece of stock I have, so I needed something that would stick out because I don't normally do really long stock, but let's give this a shot and see what it looks like. There we go. And there you go. So I didn't get this perfectly centered, I just put it in real quick. But the goal is not to have it flop around, especially if you're going for high RPMs. Alright, thanks for watching. Hope to see you next time.